Oh, sorry. Can I introduce you? Photo-initiated chemistry in single levitated aerosol droplets with cavity ring down spectroscopy. So, Zhang, thank you very much.
Thank you. Morning, everyone. Today I'm going to talk about my PhD project, which is about the photo-initiated chemistry in single levitated aerosol droplets with cavity ring down spectroscopy. Oh, okay, thank you. So the aerosol and cloud chemistry play a crucial role in the processing of atmospheric particulate matters and a key component of global atmospheric modeling. Chemical reactions initiated by sunlight are considered to be the main cause of degradation and oxidation of substances in atmospheric aerosols. And the effect of light-absorbing organic matters on solar radiation is unclear, so it's important to investigate photochemical reactions happen in aerosols. The study on model aerosols containing dyes allows the kinetic of photochemical reactions to be explored. And it's been reported that the particle size plays an important role. Photolysis is an order of magnitude faster in submicron to micron droplet size compared to larger droplets. And this plot shows photoacoustic signals for vis-441 and tetraethylene glycol droplets as a function of time. So we could see the photobleaching of vis-441 occurs in a very fast timescale, and both the initial droplet size and the light intensity have an impact on the photobleaching rate. So vis-441 is a photoreactive dye that absorbs light strongly at 441 nanometer, and this curve shows the absorption spectrum of vis-441. We find it also shows some absorption at 404 nanometer, and the imaginary refractive index K of the solution can be simulated through the Spear-Lambert law. About extinction cross-section, the extinction cross-section quantifies the total power removed from an incident light beam, and it's a sum of a scattering cross-section and the absorption cross-section. The key quantities influencing the optical properties of a droplet is the particle size, phase, shape, and refractive index. The complex refractive index is defined as m equal to n plus ki, where n is the real part that quantifies the change in the speed of light through a medium, and k is the imaginary part describes the attenuation of the light through inside the medium. The complex refractive index is directly related to the chemical composition of the droplet, so it's possible to study the photochemical reaction kinetics by tracking the changes in the refractive index. We use the cavity ring down spectroscopy to determine if the photochemical reaction is occurring. Cavity ring down spectroscopy is an ultra-sensitive technique capable of directly measuring the extinction cross-section of individual particle. And this schematic shows a linear electrodynamic quadrupole, which should levitate a single light-absorbing or non-absorbing particle for a long time. And the part marked by this red circle is an optical cavity, which consists of two highly reflective mirrors. A continuous wave laser at 405 nanometer will go through a acoustical optical modulator, then excite the cavity. And the position of the mirrors can be adjusted slightly to achieve resonance, where the intensity of the intracavity light will increase and is monitored by the photodiode. After reaching a threshold voltage, the photodiode will tell the modulator to start a ring-down event. Then the intensity of the intracavity beam will start decay exponentially. And if there's a particle in the cavity, it will extinguish a small fraction of light, resulting in a faster ring-down decay than an empty cavity. The characteristic time for the light intensity to decay by 1/E is called the ring-down time, tau, and the extinction cross-section can be determined using the following equation, where R is the length of the optical cavity and W is the beam width. Concurrently, we have Gaussian beam output at 532 nanometer propagates vertically upwards and is incident on the suspended particle. The generated phase function is processed in real time to produce a one-dimensional variation of scattering intensity with angle. Fitting these one-dimensional variations with mean theory will give the droplet size. We also introduced a blue laser at 405 nanometer to trigger the photochemical reaction. It traveled in parallel with the blue light and is isolated by a polarizer so as not to affect the collection of phase function. At early stages, we've successfully performed cavity ring-down measurements and vapor pressure measurements on pure hexentral and a series of PEGs. The left panel shows cavity ring-down results on the 1 to 6 hexentral droplets. Those black droplets are the evolving extinction cross-section with radius, and the right line shows the best fit of predicted from mean theory. And the complex refractive index is also retrieved from this prediction, this fit. The right panel shows replicates for 5 separate droplets measurements, and they have average N value for 1.4925. As the hexentral doesn't absorb light at 405 nanometer, so only the N value is given here. In terms of the vapor pressure, if we assume the temperature at the droplet surface is the same as at infinite distance, then the droplet vapor pressure could be calculated by fitting the Maxwell equation to the time-dependent radius data. And the left plot shows the corresponding vapor pressure results for the 5 same measurements. Both of the cavity ring-down and vapor pressure measurements have a good agreement with the literature, verifying the accuracy of our experimental design. After that, we demonstrated the photo bleaching in VIS441 and hexentral binary aerosol droplets. The VIS441 and hexentral are added in water with a ratio of 1 to 10 to make an aqueous solution with a mass concentration of 0.05%. This concentration can well control the initial droplet size to be around 1.5 microns under dry condition. So the right plot is a comparison of cavity ring-down results for bleached and unbleached droplet. We could see the K value for the bleached droplet is very close to 0, indicating that the droplet doesn't absorb 405 nanometer light, or say it's bleached. Also, we could see a lot of peak structures in the bleached data size, which is caused by the effective coupling of light rays to the resonance modes of spherical particle, called whispering gallery modes. Oops, sorry. The onset of photo bleaching is very sensitive to the effective light intensity. So if we control the light intensity and the initial droplet size very close to each other between the measurements, the exposure time would reflect the extent to which the photo bleaching is happened. So this plot shows a measurement with 3 minutes of illumination time. The droplet is partially bleached based on the K value. Also, it's demonstrated by this damped resonance structure on this plot. So this part of study on VIS441 hexentral system provides the possibility to study the kinetics of photo bleaching reaction. So we decided to move to more atmospherically relevant brown carbon species. Recently, the reaction of aldehydes and nitrogen-containing nucleophiles to form brown carbon has been extensively studied, and the kinetic of imidazole formation is also reported. This schematic shows the reaction to form imidazole. Similarly, the imidazole to carboxylaldehyde is the main production of methyl glyoxal and ammonium sulfate reaction. we've performed a set of photo bleaching measurements on this imidazole 2 carboxylaldehyde and hexantrol binary aerosols. And this plot shows the imaginary refractive index K as a function of exposure time. We could see the photo bleaching degree is increasing with exposure time. This part of study is not yet completed, and we expect to populate more experiment points to get a better fit. Also, we'd like to vary the light intensity and the initial droplet size to see the impact on the photo bleaching rate and generate small data series on this plot. My future plan would be extend this experimental design to some other brown carbon species from biomass burning. For example, we'd like to see the photo enhancement in for natural catechol at 405 nanometer. That's all. Thank you. Any questions?
Thank you, very nice. And so a long time ago, we found that at least for primary brown carbon from combustion, from biomass burning, basically the lower the volatility of the, of course it's volatility, but the lower the volatility of the brown material, the browner it was as well. Now, though, I don't know whether those are imidazoles or not, but we never really got beyond just that empirical observation. It kind of makes sense in the sense that you could imagine basically higher molecular weight compounds with more conjugation and maybe more absorption. But is that anything you can look? I mean, can you get like capture things like you know, combustion aerosols and look at their optical properties with this?
Yeah, it's a really interesting question. I think the volatility is a really important properties for this brown carbon species. And so the reason I picked the full natural catechol is because it has a quite proper evaporation rate, so that we could make it stay in the aerosol phase for like 2 hours time scale, which is able to suitable for our cavity ring-down measurements. And there's another ways that we could adjust the volatility for the aerosol droplets containing brown carbon, for example, by adjusting the RH condition or doped with some other species like the things I used, the hexantrol I used here, so that we could, I think, study this kind of species in the single aerosol phase. Thank you.
Lovely talk, thank you. You mentioned that you have to polarize your blue laser so that it doesn't interfere with your particle sizing. Do you expect that will affect the bleaching in any way, or is that like not an issue?
It won't be an issue because the photo bleaching or the photochemical reactions would happen if your blue laser is incident on the particle. So the polarizer will only affect the phase or the phase you collected, because we have a camera to collect phase function. The polarizer is only used to make the blue and green laser in different phase or altitudes, so that you only collect the green laser, but the blue laser is still incident on the particle and trigger the reaction.
Cool, thank you.
Great. Shall we thank all the speakers and
Thank you.